Why were fractions invented and what is the purpose of studying them? A fraction is a number is composed of a numerator and denominator to express a part of a whole. As humans began to divide objects equally, numbers that were smaller than 1 came to be needed. However, ancient Egyptians in particular only used fractions that had 1 as the numerator. We call fractions with 1 as the numerator a unit fraction. Then, why did people in ancient Egypt only use fractions that had 1 as the numerator? This is because unit fractions came about during the process of dividing up the eye of the Egyptian god Horus. In Egypt, unit fractions are also called Eye of Horus Fractions. However, there are many differences when we compare the fractions the ancient Egyptians used and the fractions we use today. Ancient Egyptians represented fractions as the sum of unit fractions, fractions with 1 as the numerator. For example, if 3 children were to equally share 2 pieces of bread, the 2 pieces would be cut into 1/2 parts, and each child would first get 1/2 of bread. The remaining 1/2 piece of bread would be cut into 3, so that each child would get another 1/6 of the bread. Why did ancient Egyptians call unit fractions the Eye of Horus Fractions? Horus was an Egyptian god who had both the eye of a human and falcon. His right eye represented the sun while his left eye represented the moon. Horus went to war with Set, his younger brother and the god of evil, when Set killed their father, Osiris. Horus won the 80-year war, but during the process lost his left eye to Set. Set cut his eye into 6 pieces and scattered them around Egypt. This angered the other Egyptian gods, who accepted Horus as the king of Egypt and protector of the pharaoh. Also, Thoth, the god of wisdom and magic, was ordered to find and restore the pieces of the left eye. Thoth was able to do this as nothing short of a miracle. Based on this myth, ancient Egyptians considered the whole eye to be 1, and differentiated and marked the 6 pieces of the Horus eye as fractions. However, the sum of the fractions was not 1 but 63/64. 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/64 equals 63/64. The legend goes that Thoth, the god of wisdom, ended up using magic to add 1/64 to make whole 1 and complete Horus' left eye. Thereafter, Horus was revered as the greatest god of sun and sky in Egypt. In addition to the historical facts that unit fractions were used by ancient Egyptians before the Common Era, there are also a few practical advantages of expressing fractions as unit fractions. Egyptian fractions are convenient to use when making sure something is divided fairly and into equal portions when sharing with others. For example, let us say there are 8 people at a dinner who had to share 5 pizzas equally. Here, the expression of the distributed pizza in the Egyptians' fractions would be as follows: 5/8 equals 4/8, which is 1/2, plus 1/8. Thus, 4 pizzas are divided into halves and each person gets half a pizza. The remaining pizza is divided into 8 pieces, and each person gets 1/8 of a pizza more. This way, everyone gets a 1/2 piece, and 1/8 piece. This way, every one of the 8 people get the same amount and size of pizza. We could also divide 5 pizzas among 8 people so that the amount of pizza is the same, but the shape of the pieces are different. For example, we could give each person 1 5/8 piece, 1 3/8 piece, with a 2/8 piece, or a 1/8 piece with a 4/8 piece. When everyone gets different sized pizza slices, they may want to have a particular size or shape of the pizza. When they do not get the shape they want, they may feel it is unfair. Unit fractions is a convenient way of making sure everyone is getting the same amount and size. Ancient Egyptians used papyrus instead of paper. The word paper also comes from papyrus. Papyrus is a plant that grew near the Nile River, and they were used as the material for Egyptian paper, also called papyrus. There was no technology for making high-quality paper, and papyrus was stiff and not as soft as the paper we have today. Still, the papyrus served as a great material for Egyptians to write on. Eames Papyrus is a document by Egyptian scribe Eames recording 200 years' worth of mathematics up to his time at around 1550 BCE. It was recorded on a 5.5 meters tall and 33 centimeters long piece of papyrus. It also came to be known as the Rhind Papyrus after Alexander Henry Rhind from Scotland bought the Eames Papyrus, and the British Museum came in possession of it. Alexander Henry Rhind, a Scottish antiquarian, bought a papyrus discovered in the ruins of an ancient Egyptian building in 1858. 5 years later, Rhind passed away and the British Museum bought the papyrus. Today, the papyrus document in the British Museum is 199.5 centimeters long and 33 centimeters tall. The original document, as we have mentioned earlier, is 5.5 meters tall, but it is presumed that the raiders sold the original document after cutting it into two parts to get more money out of it. The rest of the papyrus was discovered later in 1922 in a collection of the New York Historical Society. The ancient Egyptians left behind numerous records on papyrus. Among them, Rhind Papyrus with its mathematics-related writings is famous. Rhind Papyrus is said to have been discovered in a Thebes ruin. There is a table with a list of fractions and 87 mathematical questions on the Rhind Papyrus. Multiplication at the time was very different from how we do calculations today. We can assume that ancient Egyptian mathematics was very advanced, in that not only that they often used unit fractions, but also that they dealt with various math problems. There are 4 main themes on the Eames Papyrus. There is a title page, writings on the ancient Egyptian arithmetic, ancient Egyptian geometry, and many other problems. When we look closely at the papyrus, we notice that it is numbered from 1 to 87. Problems from number 1 to 84 deal with mathematical content, but numbers 85 to 87 describes the historical period right after the papyrus was written. The content in the papyrus is not original. It contains content on how it was copied off of what was written on other papyruses. This allows us to assume that papyrus was a guidebook to educate apprentice scribes on mathematics, and that it is based on advanced learning material passed down from previous generations. The fractions we use today are used in many different ways. First, fractions represent parts of a whole. For example, let us say there is a whole loaf of bread fresh out of the oven. Even before it cools, we slice it up quickly into 8 equal pieces and eat a certain amount to have 3 pieces left. Because 3 out of the total of 8 pieces are left, we can express this as a fraction by putting the number of pieces left 3 as the numerator and the total number of pieces 8 as the denominator. In other words, the amount of the loaf of bread left is 3/8. Second, fractions also represent the quotient of a division of natural number divided by a natural number. Let us say there are 4 candies. If we were to share the 4 candies among 3 people, how much should each person have? First, we can each get a whole piece of candy, and the remaining candy has to be equally divided into thirds, so each person can get an additional 1/3 of a candy. This is just like the division, 4 divided by 3, so when solving for the quotient of a division, fractions also play an important part. Third, fractions are also used to figure out how big or small a natural number is. Let us say there is a 10 centimeters long pretzel stick. If we ate 3/5 of the 10 centimeter pretzel stick, how many centimeters did we eat? What we are trying to calculate is the length of 3 pieces of the pretzel stick after it has been cut into fifths. We can get the length with the formula, 10 centimeters times 3/5 equals 6 centimeters. Likewise, fractions show the size of a natural number. So, what are fractions? And what is the purpose of studying them? Fractions is a way of counting a part of a whole. Fractions are expressed by writing a number on top and another on the bottom and drawing a line between the 2 numbers. The number above the line is called a numerator, and it represents how many parts are accounted for when the whole is divided equally. We call the number under the line a denominator, and it shows how many equal pieces we divided the whole into. Thus, in the fraction, 1/5, 5 is the denominator, and it shows the whole was divided into 5 equal pieces. 1 is the numerator, and it shows that we are referring to one part of 5 pieces. Looking back at human history, the need to count came about as the concept of ownership developed, and the need to distribute things equally naturally brought about the need for fractions. What are the characteristics and logical reasoning that the many different kinds of fractions have? The concept of numbers came about as people started to own and trade livestock and grains. However, different tribes had different ways of counting. For example, some tribes simply counted to 2, 1, 2, and everything more than 2 was regarded as many. Other tribes counted the number of sheep they had by drawing a line on a tree per sheep. However, because different tribes had different ways of counting, it was inconvenient when comparing or calculating the number of livestock. That is why numerals came about. Primitive people could count and remember the number of objects without numerals by associating the objects with their fingers and different parts of the body. The picture on the right shows an example of counting from 1 to 22 using our body by starting from the little finger on the right hand and going around the upper body. However, with this method, it is easy to lose count when there are more than 22 objects or the counted subjects are moving animals. This led to the improved way of counting that corresponding every sheep to a small pebble. The South American Incan tribes kept accurate records by tying many strands of pendants on a thick string made using common wool or cotton. Another auxiliary string was hung on each pendant string to make a knot. The different size and location of the knots represented different numbers. The strings were also color-coded. For example, gold color strings represented gold, white strings represented silver, and green strings represents grains. In addition, Kipu, a system that expressed numbers through knots, was used for calculations. The wisdom of the Incan people that used knots to express numbers at a time where there were no letters or numerals is remarkable even today. However, this method of counting was not suitable to share with other tribes. The concept of numbers existed even before people started to record their lives and passed it on to others. How did the ancient people understand numbers? How did they do calculations? It is difficult to say for certain, but we can speculate how they understood numbers by looking at their lives at the time. People in primitive societies got food mainly through hunting and gathering. Because the main priority was to get everyday food, there was no need for an accurate numbering system. Once they started to in groups, the concept of numbers came about. Of course, the concept of numbers was not as sophisticated as it is today, where we can specifically state how many of something there is. It was at an elementary level where they could identify whether the subject they were counting increased or decreased in number. Research shows even animals can recognize whether there is much or little of objects on an approximate level. As societies developed, the concept of numbers became more concrete. Tribes, which lived in family units, now needed to know how many members they had, how much livestock they had, and how many of their enemies were out there. The concept of numbers was necessary for their survival. Today, Arabic numerals allow us to record and calculate numbers. Then, why do we have to study the concept of numbers and the method of calculations used in the past? Numbers did not come about overnight, but it developed and changed throughout history to become how we know it today. Math is not just about solving problems through formulas. We also have to understand how the mathematical concepts came about and how we can apply it. The abstract concept of numbers is actually the best result from observing nature. Once we understand the development of numbers, we can recognize the secrets of nature to some degree. This is why we study the process through which such fractions were made through fractions. Mathematics first started with observing and understanding nature. As the center of mathematics moved from ancient Egypt to ancient Greece, mathematics became more logical and human-centered. Although mathematics started in the process of understanding nature through the acquisition of nature, as studies on humans and society flourished during the Greek era, mathematics came to a stagnant period for some time. Anyhow, the ancient Egyptian mathematics focus more on additions that are much simpler than multiplications. That is, Egyptian papyruses shows how to do multiplications or divisions by squares or additions. Egyptians were skilled at using fractions, used them to do additions. Another characteristic of Egyptian mathematics to consider is that they did not differentiate between exact numbers and approximation of numbers. This is quite ironic considering that their large-scale architectural structures were all built very precisely. The ancient Egyptian mathematics, which we have come to understand through the Eames Papyrus, seems extremely limited and basic. Still, ancient Greeks considered Egyptian mathematics as the source of their mathematical knowledge. This is why ancient Greek mathematicians, such as Thales and Pythagoras, often traveled to Egypt to study mathematics. There is no doubt they learned more than what is recorded on the Eames Papyrus. The Library of Alexandria probably stored a lot more papyrus that contained vast and detailed content on the structure of general knowledge. It is a pity that they all disappeared when the library was destroyed. Alexandria was a city founded by Alexander the Great in 330 BCE. It was then ruled by Ptolemy I Soter until 30 BCE when the Romans conquered the city. Ptolemy I, who had been a subordinate of Alexander the Great, built the Mausoleum. His son, Ptolemy II Philadelphus, built a library in the Mausoleum based on studies Aristotle personally collected. It is said that when Ptolemy III Euergetes succeeded the throne, he had collected scrolls, historical records of humanities, and books, amounting to over 500,000 books and scrolls in the library. However, this library was destroyed 3 times. It is said to have been first destroyed by Julius Caesar in 47 BCE, then by a group of Christian enthusiasts in 391 AD, and finally in 640 AD by a Muslim caliph. Of course, it is said there were other libraries in Alexandria, so the number of books in the library built by Ptolemy III may be less than what remains to this day. As time passed by, with the plunders from greedy collectors, fire due to earthquakes, and never-ending wars, the Library of Alexandria slowly disappeared, and the location of the Mausoleum was buried into legends. We have already mentioned that out of the 87 problems in Eames Papyrus, 81 of them are about fractions. The ancient Egyptian fractions, the Egyptian method of calculating using, is considered to be the most notable component of Egyptian arithmetic. Egyptians only used unit fractions. Unit fractions are fractions with 1 as the numerator, such as 1/2, 1/3, and 1/56. However, one of the fractions used by the Egyptians, 2/3, was not written as a unit fraction but expressed with a special hieroglyphic character. Egyptians expressed fractions that were not unit fractions as a sum of fractions with different denominators. For example, 2/40 was expressed as 1/42 plus 1/86 plus 1/129 plus 1/301. Also, when adding unit fractions, duplicates fractions were not used. How did ancient Egyptian math get specific unit fractions when fractions are expressed as the sum of unit fractions? Why did they express fractions as the sum of unit fractions? One thing that is clear is that there were many different ways of adding unit fractions to get 2/43. How did ancient Egyptians know the specific unit fractions and why did they decide to use them? As we can see in the Eames Papyrus, the unit fractions needed for the additions did not need to be solved for. The Egyptians had a mathematical table that listed ways of adding non-repeating unit fractions to come up with fractions that have 2 as the numerator and odd numbers 5 to 101 as the denominator. Because they only used unit fractions, which have 1 as the numerator, they did not feel the need to use numerators. This is why fractions were expressed with an oval over the number for the denominator. Some fractions, such as 1/2 and 1/3, were expressed with special hieroglyphics. 1/2 is a symbol of the hieroglyphic of a cloth folded in half, and 2/3 is a symbol of an oval with 2 short lines hanging under it. Let us return to what we were discussing before to further develop the story of fractions we use today. Fractions are the numbers that represent the amount of number compared to a given number. Suppose a tree planted this year is 2 meters tall and a tree planted last year is 5 meters tall. If we consider the tree planted this year as the base, the tree planted last year is 5 halves tall, and if we consider the tree planted last year as the base, the tree planted this year is 2/5 tall. Likewise, fractions can be used to express relative size with a number as a base. In addition, there are many different types of fractions, such as proper fractions, improper fractions, and mixed fractions. A proper fraction is a fraction where the numerator is always smaller than the denominator. Thus, a proper fraction is always greater than 0 but less than 1. There are also fractions where the numerator and denominator are the same or the denominator is larger than the numerator. These fractions are called improper fractions. An improper fraction is always equal to or greater than 1. A mixed fraction is a natural number and a proper fraction put together. Mixed fractions and improper fractions can switch forms with each other because they have many similarities. So, when comparing or calculating fractions, improper fractions can be switched to mixed fractions or vice versa to help solve problems more easily. What would natural numbers converted to fractions look like? For example, what would the natural number 1 look like as a fraction? This question is asking us to find a fraction that is the same size as the natural number 1. In order to answer this question, we just need a fraction that has the same numerator and denominator, such as 2/2, 3/3, 4/4, and 5/5. Fractions equal to the natural number to are fractions where the numerator is always the double of the denominator, such as 4/2, 6/3, 8/4, and 10/5. And fractions equal to the natural number 3 are fractions where the numerator is always triple the denominator, such as 6/2, 9/3, 12/4, and 15/5. Likewise, when we convert natural numbers into a fraction form, the numerator and the denominator are equal or it is always an improper fraction, where the numerator is larger than the denominator. Now let us compare the size of fractions. What is an easy way to compare the size of fractions? First, take a look at proper fractions that are easy to compare. If denominators of two proper fractions are the same, the proper fraction with the larger numerator is the greater number. For example, if 2/5 and 3/5 have the same denominator 5, 3/5 with the numerator 3 is larger than 2/5 with the numerator 2. If denominators of two proper fractions are different, we can compare their size by getting a common denominator. For example, we cannot compare the size of numerators in 2/3 and 3/5 as they are to determine the size of the fractions. In this case, first, two fractions need to be reduced to their least common denominator 15. We can then compare their size. 2/3 equals 10/15, and they are greater than 3/5, which is equal to 9/15. Even if we are dealing with improper fractions, we can compare the size in the same way as we compare the size of proper fractions. First, check if two denominators of improper fractions are the same. If they are the same, the improper fraction with the larger numerator is the greater fraction. If they are different, the size of the two fractions can be compared after reducing them to the common denominator. What do we do when we have two mixed fractions? Because mixed fractions have natural numbers, we have to compare the natural numbers first, unlike proper fractions or improper fractions. When comparing two mixed fractions, the one with the larger natural number is the greater fraction. However, if they have the same natural number, we need to look at their fraction part. In this case, we can compare the size in the same way as we do for proper fractions or improper fractions. For instance, by comparing the natural numbers in two mixed fractions 3 and 2/3 and 5 and 3/5, we can easily see that 3 and 2/3 is less than 5 and 3/5. However, when the natural numbers are the same, as in 3 and 2/3 and 3 and 3/5, we find 3 and 10/15 is greater than 3 and 9/15, only after reducing two fractions to the common denominator. Lastly, what should we do when we compare two different types of fractions, like comparing improper fractions and mixed fractions? In this case, we can compare the size after converting them into either improper fractions or mixed fractions. As such, if it feels difficult to compare the size of fractions because they have a different type of fractions, this problem can be easily solved by converting them into the same type of fraction. Comparing the size of unit fractions used in ancient Egypt is somewhat different from comparing the size of proper fractions. We should not think that unit fractions do not have numerators that we can compare, since their numerators are always 1. When we compare the size of proper fractions with the same denominators, all we have to do is compare the size of numerators. However, when it comes to unit fractions that have the same numerators, we have to compare the size of denominators. What is remarkable here is that unit fractions become greater as denominators become smaller. This is because the numerator, a part of a whole, increases as the denominator dividing entirety decreases. How could we use isotopes, which reflect fractions? Fractions are the numbers that represent the amount of number compared to a given number. A half-life is the time required for the entire atoms of radioactive substances to be reduced to half. Whether a nucleus will decay or not is a question of probabilities. Let us talk about what we mean by probabilities here. A probability is a numerical value representing chance events or things that are uncertain. For example, when throwing dice, we never know what numbers would come up on the next roll. However, suppose that we know the number of times each side came up on top after throwing a dice thousands of times. This means that we could predict that each side would appear the same number of times when we throw the dice the same thousands of times. In other words, we could predict the number of dices showing a given number when we throw thousands of dices. Of course, it is impossible to know exactly which dice will show a number. Now we may understand the meaning of probabilities. We could intuitively know that a half-life required for the amount of the nucleus to be reduced to half is always constant as long as there are enough nuclei, regardless of the number of nuclei remaining. If the number of nuclei was 100,000, which was reduced to 50,000 nuclei, this is equivalent to the time it takes for 50,000 nuclei among the 100,000 nuclei to decay to 25,000 nuclei. Thus, it takes the same amount of time for 50,000 nuclei remaining to become 25,000 nuclei. Just as we can calculate the age of trees by observing tree rings, there is a way to figure out the age of fossils or rocks. This has been possible by radiometric dating method. This method uses materials known as isotopes to determine the age. Most carbons consist of 6 protons and 6 neutrons. Some carbons have 6 protons and 8 neutrons. As such, the elements with the same number of protons but with the different number of neutrons are called isotopes. Because isotopes are unstable, they share a common property that they try to decay to become stable. Scientists have discovered that the time it takes for atoms to decay is constant. The radiometric dating method uses this principle. Carbon dating method is the most frequently used method among them. The carbon dating method is used mostly to measure the age of artifacts containing organic materials. If an animal or a plant dies, unstable carbon-14 contained in the body start to disappear. Carbon-14 is said to reduce to half every 5,730 years. The time required for neutrons to reduce to half is called a half-life. The number of neutrons in unstable carbon-14 decreases over time, but that of stable carbon-12 does not change. Using this property, we can calculate how old artifacts are by comparing the ratio of carbon-14 to carbon-12. Not only carbon, but also other isotopes have the same property. Scientists use a variety of isotopes to calculate the age of old artifacts or fossils. However, the radiometric dating methods are discredited by some scientists. This is because a half-life could vary depending on the environment. Besides, the way of measuring age cannot be trusted since we do not know the initial condition. Another reason why the radiometric dating method loses its credibility is that there have been many cases where errors caused failures in the measurement.